So, hello everybody, my name is Wolfgang Woiwode, I'm from KIT in Germany, and I will present you a selection of airborne FTIR limb emission observations, and with these observations I will try to provide you a glimpse of what can be expected from the next generation of spaceborne limb imagers. And first of all, I would like to mention that the studies that I will show you were made possible by many people from the MIPAS and Gloria teams at KIT and in Jülich, and also other partners at KIT, Jülich, DLR, and further partners from other institutes in the framework of aircraft missions. So, the goal of my presentation is to show you examples of studies involving observations by the MIPAS SDR and Gloria limb sounders. I will illustrate how these observations access smaller scales and supported atmospheric research. I will compare some of the results with spaceborne observations by the MIPAS instrument on Envisat, which is well known. And with that, I will provide a glimpse of what can be expected from future missions, such as the Earth Explorer candidate CARED, based on real observations. And of course, I would like to mention, I will show only a few selected cases here. There have been many other important studies and important instruments that are not mentioned here. Since MIPAS plays an important role in my presentation, I would like to start with a short overview on the family of MIPAS instruments. So there was the MIPAS instrument on board Envisat. Here you can see some of the geolocations of the limb observations by MIPAS, going up to 80 kilometers here. Then there were the MIPAS balloon observations. Here is a picture shown of the balloon in the gondola, reaching altitudes of up to 40 kilometers. And with these observations, you can follow air masses and look into different directions. And then there were the MIPAS STR observations on the Geophysica. Here a flight track is shown together with the tangent points of the MIPAS STR observations, reaching an altitude range of up to approximately 20 kilometers. There were further MIPAS instruments, so the MIPAS on the Transall aircraft and the ground-based MIPAS instrument, which are not shown here. And since with the aircraft observations we have the opportunity to sample large parts of a satellite track, the airborne observations are in focus in my presentation. So we start with MIPAS STR. So it was the airborne version of MIPAS instruments. So it consisted of a double pendulum interferometer, a cool detector, a telescope, and a scanning mirror, and performed conventional limb sounding. So different altitudes were scanned again and again. And this instrument provided one profile within less than 3 to 4 minutes, depending on the scanning mode, resulting in horizontal sampling of approximately 25 to 45 kilometers. And the instrument provided beautiful spectra. So here the channel 1 is shown at a high spectral sampling of 0.036 centimeters to the -1. These are examples of Arctic ozone observations during the Reconcile campaign in 2010 in March. So up here you can see a flight track of the Geophysica from Svalbard going to Kiruna in Sweden. And here you can see the tangent points of the MIPAS STR limb observations. Down here you can see a single profile retrieved from the MIPAS STR observations, so the black profile that you can see here. The gray profile is the initial guess and a priori profile, which looks very different. And the MIPAS STR profile really nicely agrees with the in situ observations, which are shown here in red. And we obtained here a vertical resolution of mostly 1 to 1.5 kilometers. Here on the lower right, you can see an comparison with in situ observations at flight altitude along the flight track. And again, the MIPAS STR observations are in close agreement. They even show many of the details that are shown in the that are seen in the in situ observations. So a really nice agreement. And if we put all of the MIPAS STR profiles together, we get such a vertical cross-section, such as shown here, where we can see details on mesoscale, so with horizontal extensions of less than 100 kilometer and a vertical extension of approximately 1 kilometer. So this really shows that FTIR limb observations can resolve mesoscale structures with high accuracy. Now we switch to MIPAS on board NVISAT. So I think this instrument is well known. Just to briefly remind you, it was a limb scanner in operation from 2002 to 2012 on the ESA satellite NVISAT. It was operated in the full resolution mode from 2002 to March 2004, and then in an optimized resolution mode. In the full resolution mode, spectral sampling was 0.025 centimeters to the -1, and a horizontal sampling of 500 kilometers was obtained here. And in the optimized resolution mode, there was a coarser spectral resolution resulting in a more dense horizontal sampling of approximately 410 kilometers. Now we compare the sampling of MIPAS STR and MIPAS on board NVISAT that you can see here. So that flight was done in the late vortex. So here you can see the polar vortex edge, which was sampled by both instruments. And here you can see a vertical cross-section, altitude versus latitude, showing the sampling of MIPAS NVISAT and MIPAS STR. You can see that the sampling of the MIPAS STR profiles is approximately factor of 10 denser than from MIPAS NVISAT. And so this gives an idea of what a denser sampling of a future limb imager might provide in terms of detail. So here I'm showing sampling, so this is not the retrieval grid, it is a sampling grid. We do not have a perfect match. We have a time lag of approximately 1 hour and different viewing directions, but we can do at least a qualitative comparison here. So here we have ozone along that track, which I've shown you before. Here on the left-hand side, MIPAS NVISAT, on the right-hand side, MIPAS STR. We did not apply any 2D averaging kernels or so to the MIPAS STR observation. We just compare as it is. We really have a very good agreement between both observations. We see all the main structures that are seen in the MIPAS NVISAT data, also in the MIPAS STR data, but in the MIPAS STR data we see much more detail, and this really proves or illustrates that the same technique in combination with a denser sampling can resolve noticeably more details under suitable conditions. The situation is getting even more dramatic when we look at nitric acid. So here on the left-hand side, again, the MIPAS NVISAT data, on the right-hand side, MIPAS STR. We can see a big filament here on the right-hand side. We can see further structures. We have a nice overall agreement again, but here in the MIPAS STR data, we can see much more detail. So further filaments, fine structures, and here in the vortex, we can even resolve a nitrification layer, which naturally cannot be resolved by the coarser sampling of MIPAS NVISAT and the coarser vertical resolution. This is the same section which I've shown you before, but going up to 50 kilometers. So here MIPAS NVISAT, here again MIPAS NVISAT with an overlay of MIPAS STR. And this is just to illustrate with aircraft observations. So these observations are just episodic observations, and we are only able to reach the lower rim of the denitrification layers. And so it would be really nice to have such detailed observations up to higher altitudes to support process studies. This is an example of Arctic polar stratospheric cloud observations during the ASCENS campaign in 2011. So briefly here, you can see the flight track. Most of the flight was in the vortex. Here we had positive PSC detections. And with these observations, I would like to illustrate the versatility of FTIR limb emission sounding. So we had information on the gas phase composition. So here you can see gas phase nitric acid and the nitrification layer directly below the flight path here. From the spectra, which were scratching at the lower rim of the polar stratospheric cloud, we could infer information on the particle composition. We really could show that these particles consist of beta nut and that these particles are probably very aspherical. And furthermore, we could infer information on the particle size distribution, which is shown here. So we started with an in situ size distribution. We did radiative transfer calculations, came up with an improved size distribution, and we could compare this with the CLAMS model showing here. And this shows you that the models still have difficulties to resemble such large particles. as observed by the in situ and the remote sensing observations here. In a follow-up study, we used this, what we have learned, to do a first vortex-wide detection of large NART particles during an entire Arctic winter, which is shown here. So briefly, you can see a map of the northern hemisphere. The blue triangles are positive detections of large NART particles. And it is a nice agreement with the temperature shown here in magenta, which shows the approximate existence temperature of nitric acid trihydrate. Now we switch to Gloria on board HALO. So Gloria is an example of the next generation limb imagers, which we hope to get in space soon. So the instrument, so it stands for Gimbal Limb Observer for Radiance Imaging of the Atmosphere. It was developed by KIT in Jülich. It is operated in 2 different, or can even operate in more spectral sampling modes. Here I will focus on the spectral high resolution mode with a resolution of sampling of approximately 0.06 centimeters to the -1. I will show you HALO observations on this aircraft here. So Gloria sitting in the belly pod here, reaching altitudes of approximately up to 15 kilometers. And we can get high vertical resolutions of a few hundreds of meters. And so Gloria records limb images along the flight track, and with these limb images we cover all vertical angles at the same time. We do not need to scan anymore. Each pixel records an interferogram. The interferograms are transformed into spectra. The spectra of the rows are averaged, and so from one data cube in the high spectral resolution mode within 3 kilometers, we get a full set of spectra we can use for the retrievals of trace gases. And it has been deployed on board the Geophysica, the HALO aircrafts, and stratospheric balloon, and served as a demonstrator for Earth Explorer candidates, such as KERT. So now I would like to show you a case study on observations of the mesoscale fine structure of a tropopause fold over mountains. So this flight was done above Europe. Here you can see meridional cross-section of IFS data across Europe. Here we had a tropopause fold. Here you can see the dynamical tropopause in red, and this tropopause fold was located at the polar front jet stream. And into this region here, we took a closer look with the Gloria observation, and that you can see here on the right, in the upper right. So this is water vapor retrieved from the Gloria high spectral resolution observations. And we really nicely can see how stratospheric air is wrapped around the jet stream and extrudes down into lower stratospheric altitudes. So these observations really confirmed the conceptual model of a tropopause fold that was developed by Shapiro and colleagues in the 1980s. We compared these observations with ECMF IFS data at a high horizontal resolution of approximately 9 kilometers. And we can see a nice agreement in the location, in the timing, and in the absolute mixing ratios. But we also see there are differences in the fine structures, and there's a slight moist bias in the IFS data, which is well known. So this really demonstrates that we need such observations to test and validate models, and this really shows that mesoscale fine structures can be resolved by limb images. Here's another case study from the other side of the world. So these were observations during the South Track campaign in 2019 from Terra del Fuego in Argentina. Here we studied the merger of the polar front jet with the subtropical jet, which caused gravity waves. We combined the Gloria observations with ALIMA LiDAR observations by the colleagues from DLR to get a wide vertical coverage. Here you can see temperature perturbations by gravity waves derived from the Gloria and ALIMA observations in comparison with IFS data. This really confirmed that the structures seen in the IFS data are realistic, and corroborated by this way further analysis of wave excitation using IFS data. And yeah, so here this really illustrates that it is important to have a high vertical coverage to do such studies. So to summarize, so here is a table with a lot of numbers. I don't want you to read all of them. All of these instruments I've been talking about have roughly comparable spectral ranges, roughly comparable spectral sampling. So the MIPAS SDR observations have illustrated that that FTIR sounding can be very accurate. We can see mesoscale structures. The comparison with MIPAS Envisage showed that using the same technique in combination with a denser sampling allows us to resolve much more fine structures. The Gloria observations have shown that limb imaging works really well, and that under suitable conditions, even mesoscale fine structures can be resolved. And so the combination of these observations provides us a glimpse of what can be expected from future missions, such as the Changing Atmosphere Infrared Tomography Explorer that has been proposed to ESA for Earth Explorer 11. And such observations would be really helpful to support atmospheric process studies and model development. And with that, I thank you for your attention.